Now, as I mentioned already, that a spatial database is a database that stores spatial objects. And it doesn't just store them, it gives you an ability to manipulate those spatial objects. What do I mean by manipulating the spatial objects? I mean writing queries that are spatial in nature. So what is an example of a spatial query? Well, when you ask, who's closer to me? That's a spatial query because it's based on location. When you ask, where is the nearest hospital to me? Or where is the nearest hospital to this building? Okay? Or where is the nearest ambulance station point? That's a spatial query. Okay? It's all related to location. Or when you ask, when does this street intersect with that street? Like, for example, when does Makram Abeid intersect with Nahas in Madinat Nasr? Okay? So that's again spatial. Or when you ask, does this compound overlooks or touches this street? Okay? Like, for example, if you ask, does the seat exist on the Shari'a Tis'een? Okay? So again, that's a spatial query. It's related to location. Now, so let's talk about each of the two components, spatial data and spatial queries separately. Spatial data is basically any data that describe location or shape and location. Okay? So I have listed here for you some examples. Some of them will make sense right away. Other ones you will be a little bit surprised that they are actually spatial in nature. Okay? For example, if you ask, what's the closest fire hydrant location to me? Obviously, you're asking about location, so this is spatial. By the way, if you don't know what's a fire hydrant, in the cities abroad, they would have a tube system that goes underground throughout the city. And you must have seen this in the movies, and there is an outlet that exists in many locations, almost in every major street. And when you get a fire, when the fire ambulance arrives, they just plug their tubes into the fire hydrant in the ground to get high pressure water right away pumped into the fire. Now, roads, rivers, streets, lakes are all spatially encoded. Okay? You cannot talk about a lake without mentioning its location, and that's spatial data again. Okay? So either describing a location or the shape in the case of a lake, because you cannot say where is the lake unless you specify its shape, and consequently the location of the lake and the shape of the lake is considered both as spatial data. Now, again, how do you represent this? Okay, we already understand now that locations or shapes of objects in a specific location is included as spatial data. But how do you represent this inside a computer or inside a database? Okay? Well, if you're talking about a location, you're referring to a specific point. Yeah, for sure, the location could cover a large area, and then we will not talk about it as a point, we will talk about it as a polygon. So if I'm referring to the fire hydrant, that's probably a point on the map, some X and Y on the map that refers to exactly where is that. Or if I'm, for example, referring to the intersection point of two streets, that's a point on the map. So anywhere where I could store a point, X and Y, or X and Y and Z if you'd like to introduce height, that would be how we represent a spatial point, X, Y, and Z. Now, if you think of a road, or if you think of a street, the street and how it turns right and left, if we're trying to store it in a spatial database, it will be a line, or more accurately, a series of vectors connected together to describe where the street is flowing inside the city, or where is it passing inside the city. Okay? If we talk about a piece of land and we would like to find out its location, the land could take any shape. And consequently, a polygon will be the most appropriate type, since you could have a polygon to represent any shape. So, in summary, there are three basic data types used to build spatial data, or to encode spatial data, or to store spatial data. Points, x, y, or x, y, and z, if you'd like. Lines, which will be a series of vectors connected together, making a line, not a closed loop, okay, not a polygon, just a line. But since the line could, change direction, we will use vectors, or internally, the spatial database would use vectors to represent the line. Perhaps the line is a street or an oil tube carrying oil from one location to another. And the most sophisticated, I would say, spatial data type is the polygon. And the polygon will describe accurately any other shape we're interested to represent apart from points and lines. So, in most spatial databases, you would see at least two types, a point data type and a region data type. And usually it's referred to in the spatial world, or in the spatial kind of research area, as region, not a polygon. But really it's going to be internally presented as a polygon, okay? Or a bunch of vectors that makes a polygon, if you'd like. Now, that's the bare minimum you need to be able to store spatial data. So if you're trying to store the location of anything, or the shape and location of anything, you need point data and region data, okay? You could go to any spatial database. From now on, you know what to look for in terms of the data type. You need a point data type and you need a region data type, regardless of what they are called. They would be called different terminology is used from one database application to another, or from one spatial database application to another. But at the end of the day, you're talking about two basic types. You need to have both of them. Now, encoding locations is not done using X, Y, and Z, as I mentioned. We have an international standard that you must have seen already if you're using cell phones, which is the longitude and latitude system. So this is, it precedes obviously computers by many, many years. And when computers were invented and later on cell phones, it adopted the longitude and latitude system. Okay, so anywhere on Earth, we could encode the location of any point using this system. The idea is, you already probably know this, so I'm going to speed up here the explanation, because I know you know this. That these latitude lines are lines that go from east to west and are parallel to each other, and longitude, as the name implies, go from north to south, and they also are placed one beside the other. And in the longitude system, the lines are numbered from -180 to +180, and in the latitude, they are numbered between -90 and 90. So using the combination of two values, longitude and latitude, you could encode any location on Earth, okay? And most, historically, most spatial databases, for obvious reasons, used this system, did not use X, Y, and Z, okay? They would have a point consist of two values, two floating point values, longitude and latitude. This is again to, put a visual to what I'm explaining. The longitude and latitude are encoded here, are lines, virtual lines on Earth, and they are used, the intersection of longitude and latitude, to pinpoint any location. And since we're talking about floating point representation, we could go as accurate as we like here, okay? So we could describe a point with extreme detail, the location of a point with extreme detail, because of using of floating points. So we're not stuck to integers, of course. So between 30 and 31, we could use 30.5, 30.51, 30.52, and every time we increase one decimal value, we know what that maps to in terms of meters on Earth. So we can get very accurate description of our location. Now, what kind of spatial queries? I can already give you an introduction to that. What kind of spatial queries would be interested to execute against spatial data? We have generally a handful of query types. The first one is the range queries. So you ask about a target location within some distance. Like, for example, find all cities within 50 kilometers of Cairo. Okay? Now, so you are basically giving a range, a number, and you ask about what's within this range or what's outside this range. Okay? So that's called a range query. Now, we also have another class of queries that's called nearest neighbor queries. Now, in the nearest neighbor queries, you're not passing to the database in your query a number, like in the case of the range, but you are saying who's closest to me. Okay, like for example, find the 10 cities nearest to Cairo. Those 10 cities that are closest to Cairo could be 100 kilometers away or could be 2 kilometers away. You don't know, but you're asking who's close to me. Okay, that's the situation you will be in if you're asking for an ambulance. Okay, you cannot tell me like, when you're trying to fire a query to find the closest ambulance because you just had an accident, la qadar Allah, is like, okay, I would like to find the closest ambulance to me within 50 kilometers or 5 kilometers. You say, where's the nearest one? If it's in the next street to me, I would like to get this ambulance, okay? So here you're asking, well, who's nearest to me, regardless of how near is near, okay? Or the reverse, who's far away from me, regardless of how far is far, okay? So typically, what you will get back is a list of result set, or a result set that consists of entries that are ordered by proximity. The closer one to you first, and then the further away and the further away. Okay? Unlike in the spatial range queries, what you get back is a result set that contains rows that are within the distance you've specified without any particular ordering usually. Okay? As long as they are within, you will get it back in your result set. Okay? Now, the third type of queries is what's called spatial join queries. Okay? Like, for example, find all pairs of cities in Egypt within 200 kilometers of each other. Now, since we're saying within 200 kilometers of each other, I'm going to join on the table of cities in Egypt to be able to answer this query. Okay? So you can here draw parallels between this type of join and the join you have learned in database 1. Okay? Now, just like all types of joins, it is an expansive operation. Okay? And in this case, it's actually quite an expansive operation because it will involve regions and proximity as well. Okay? Because you're saying within 200 kilometers. Okay? So you are actually going to do more involved calculations here than what you expect, and we will see that later on. So these are the type of queries that you could be firing against a spatial database or a spatial data type. So I have here a number of examples, just again to make you think deeply about spatial databases. Okay, showing you many applications of spatial databases. For example, transportation engineers, and transportation engineering, by the way, is a branch of civil engineering. They study the flow of traffic in streets. Where should bridges be built? Where should tunnels be built? Where should the subway passes? And so on. In order to do that, they model the streets in a city as a graph of roads, where the streets represent roads, and the roads, or the streets and roads, are represented as lines, and the bus stops and intersections are actually points. And then they do all kinds of analysis, on such a representation. So all their work really is firing, or involves firing, spatial queries. Like, for example, if you would like to go from this street to that street, what streets should take you there, or can take you there, okay? Or in other words, if you'd like to think of it in Uber terms, which is the fastest path from your starting point to your destination? So the underlying data structure you're working with is going to be more or less something that looks like what we are seeing here, where the streets are modeled as lines inside the database, inside the spatial database, and the intersections are going to be modeled as points, and you have to figure out how to go from one starting point to some final destination by firing spatial queries. Now, spatial databases are not just used in applications like Uber. In fact, the earliest customer of spatial databases around the world were governments, because to collect taxes, to do proper administration of municipalities and of natural resources such as rivers and lakes and agricultural land, a basic requirement is to know the location of these objects. And spatial databases is all about storing locations and shapes of objects. So what you're looking, for example, here at is a typical usage of a spatial database where the different pieces of land is stored in a spatial database with the shape of every piece of land and its location. Now, this is how usually governments conduct proper governance by tracking data, by storing and tracking data. So the different colors here would mean different things. For example, different agricultural crops planted there. The blue areas could be a river or a lake. Okay? And the boundaries of this are all stored in a spatial database. Even administrative divisions are encoded spatially. So this is the same map we were looking at before, with the area under every municipality is labeled with the borders between them. Okay? So it's used in agricultural planning, it's used in economic development, it's used also administratively and legally to set the boundaries between different counties and different provinces and so on. And that's why, again, as I mentioned, governments, starting from the 1950s, was very interested in spatial databases, because this is how they can properly run the resources in the country and consequently the economy of the country, by tracking things down to where is this piece of land, what's planted there, where does it exist in terms of the administrative region it belongs to, and so on. So the takeaway: spatial data describes location and area information using geometric data types, lines, polygons, etc., as well as global positioning system, GPS data, aka longitude and latitude. Now, let's dive a little bit more into this notion of spatial queries. Spatial queries are actually querying about or asking about the spatial relations between spatial data. So when you store spatial data, you're going to be storing it just like you store any piece of data, kind of row-wise organization inside a table. But between the different spatial data that you are storing, there are three basic relations that either is stored directly inside the database engine or retrieved through a query. Okay? The most basic relations are proximity, adjacency, and containment. Okay? So proximity obviously involves some kind of distance calculation. Adjacency involves a Boolean check whether two regions or polygons are touching or overlapping or not. And containment is asking another Boolean question, another conditional statement, whether one area is within another area or overlapping with it. Okay? So let's talk about this more. This is an example of proximity. Now, I hope now you see why this is getting a little bit more sophisticated than what you would initially think, because your initial thinking could be like, this sounds too simple. Actually, sometimes it's not. Like, for example, here. If you look at this map of regions or plots, if I ask what is the shortest distance between those two plots colored in red, and the answer is not straightforward, because you will have to find the point that is closest on the two sides. So you cannot, for example, measure it from any location. It has to be the 2 points I've connected with a cyan line. And this will give you, that cyan line is actually the shortest distance between the two red regions. Okay? Any other 2 points you pick on both sides, one from this red plot at the bottom left, and another point from the red plot at the top right, will not give you the shortest distance. So if you ask what's the distance between, or what's the shortest distance between those two red plots, you have to calculate it using the angles or the corners that I have used here to draw the cyan line. Okay? That could be an important question, like, for example, what I posed here. You know, you're interested in distance between a waste dump and a piece of property you were considering buying. So if someone tells you it's that far away, but it's not, because they used a different reference point in each red plot, that will give you a false distance. Okay? So if you ask here, you're really asking about how close is the waste dump to your area, your desired plot, or the plot you intend to buy. Okay? So this is an example of proximity, how close. Now, also, proximity could be used to ask a basic question: how close is, or the distance to some shop you're interested in. Let's say you're interested in getting a cup of coffee, your morning coffee, and you like Starbucks. So you need to find the closest Starbucks to you, okay? But that involves measuring the distance from where you are to all the Starbucks in your neighborhood or in your city, sorting the result set and getting the one that's closest to you, okay? So this involves distance calculation from where you are to every one of the Starbucks in your area. So this is again an example of doing distance calculation. Notice here that this distance calculation, just like in the previous slide, is not respecting the streets. In other words, this is a straight line distance. But if you actually calculate the distance through, or if you'd like to know the distance between you and the closest Starbucks, but you're talking about the driving distance, which means it's the distance you're going to travel through the streets, that's going to be something else. You cannot answer with this type of proximity query. Because here proximity is using longitude and latitude, your longitude and latitude, and the longitude and latitude of every one of the Starbucks to get a straight line measurement. But if you're interested to actually follow the path through the streets, that's something else. You cannot do with proximity. You will do with the other ones. You will answer it with the other types of queries we're going to talk about. Here is the one that actually you could use recursively or repetitively to get the answer to the question I was posing in the last lecture slide. Now, this is another type of query which is called an adjacency query. Now, in the adjacency query, you're asking basically who's connected to me directly, or whom I am sharing an edge with. Like, for example, here, if you're interested in the yellow plot, you would like to know who are your neighbors. Now, your neighbors are many plots, all the ones labeled in red. So if you try to count them, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 neighbors here, okay? The query that you ask, the spatial query type that you ask here is called an adjacency, which means whom I am sharing a border with, okay? This adjacency query is interesting because we could write complex adjacency queries that enable us to go from a starting point to a destination. Going through the maps, traveling through streets, by standing at every street and saying, who is this street connected to? So you get the intersecting street. And then you move on to the intersecting street and you say, who is this street connected to? So you get the intersecting streets. Because if two streets are actually adjacent to each other, this means they touch. And if they touch, then they are adjacent. Okay, so we could build very complex queries using this adjacency feature. Now, the notion of connectivity is also another way to ask about adjacency here. But what you're saying here is, where is this passing through? Is this connected or not? So connectivity is considered as even a higher level than adjacency, because internally it could be implemented using a series of adjacency queries. Okay? Now, a typical example of showing this is representing the flow of the river. The river could branch into many smaller branches, but they're all connected and they all make one river. Okay? Now, if you'd like to ask queries related to where is the river flowing, you're really asking a connectivity question. You know, who is connected to this river? Okay? And obviously, where I labeled here the with the red dots are pieces of information that you can get using an adjacency query. In fact, as I mentioned, connectivity could be answered using adjacency. Okay? So everywhere there is a red dot, that's an adjacency query, or that's an adjacency piece of information that with this branch is connected to the main river through this red dot. Okay? So now I hope you start to appreciate spatial queries, that we could use them to answer very complex, actually, types of queries. And they're not very common outside the spatial domain. So if you think, for example, of an e-commerce website, you don't ask these types of queries. You don't ask about connectivity or adjacency or nearest neighbor or proximity, okay? These queries only make sense in the context of spatial data. So the news is actually, although spatial data are very spatial in nature, they exist everywhere, from government databases to municipality databases to lawyers' offices, okay, to transportation engineering departments everywhere, to even maintaining statistics and demographic information about people. Like, for example, saying that there's only 0.5 million Egyptians living in Sinai. Okay? That's a special piece of information. It's spatially derived, because you got to figure out who is actually within Sinai. So again, that's special information. Okay? So there are many organizations that are interested in making use of spatial data. And obviously now, all the new cell phone applications that are trying to rely on your location utilize spatial data. Okay? One of the things that I get annoyed about every time I go to Carrefour, after I leave Carrefour, I get advertising messages from shops inside Carrefour. I'm referring to Carrefour, Maadi City Center, you know, Carrefour. So what that means is when I went inside with my cell phone, my number was tracked, and my location was identified, that I am inside, you know, Maadi City Center, and that is communicated somehow to an advertising agency that those shops inside Maadi City Center are paying to start to bombard me with advertisement. So this is again an application of spatial data, because if I don't go there, I don't get these messages. So it is related to my location there, or me being there. Now, let's just give you some history about how things went in the spatial database world. Now, historically, we would never cover a spatial database or talk about spatial databases in a database course, because spatial data was not stored inside databases. If you go 30 or 40 years ago in history, you would see another area another course or another even sometimes major in certain universities in the States called GIS, Geographic Information Systems. Now, the old approach to storing spatial data was to create a separate application that's called a GIS application. Again, GIS stands for Geographic Information System, and you store the spatial data there. Now, the problem is GIS systems only stored spatial data. But spatial data does not make sense or is not useful unless it gets mixed with non-spatial data. For example, the shop being Starbucks is not spatial data, it's just data. But the location of Starbucks is spatial data. Okay? The fact that this Starbucks is drive-through versus another Starbucks that is not drive-through is not spatial data. But its location is spatial data. So there was a separation between the storage of spatial data and non-spatial data. And that separation caused all kinds of problems, including introducing anomalies in the data. Okay? So, sometime passed before people realized, researchers realized, that it is best to integrate spatial data into SQL databases. So the non-spatial data and the spatial data gets stored in the same server, in the same SQL database. And since the non-spatial data is way more than the spatial data, so the choice was to integrate spatial data inside SQL databases, not the reverse, not to integrate SQL databases into GIS systems. And what happened is, spatial data got integrated as, an additional feature into the SQL databases. So just like you have learned in database 1 that there are SQL data types, like varchar to represent variable strings, there is also spatial data types that represent polygons and lines and regions and points and so on. Okay? So it's just now like any other data type that you could use inside a database. Okay? So that is the story, in short, of the history of spatial data. That nowadays, we are storing them inside SQL databases. That's why we're talking about it in this course. Now, once you store spatial data inside SQL databases, you get all the advantages of SQL databases, including things we didn't talk about yet in this course, like, for example, doing transactions, having backups, doing integrity checks, okay? Everything that you've learned in database 1 now is applicable to spatial databases, or spatial data, and everything that we talk about in this course until the end of the semester is also guaranteed for spatial data, that you're going to get it for spatial data, because now it's part of the SQL world. Now, what we also gain from integrating spatial data into SQL databases is that we are making use of the huge code base with all the features that exist in the SQL world, and we utilize what we have learned and are doing regularly in the SQL world, and we just augment that with some spatial features or spatial manipulations. So the total development time is actually much shorter compared to having a separate GIS application where we store the spatial data and we do the manipulation there programmatically by writing plugins or writing a code that connects to the GIS system to query, for example, the location of an item, and then going back and connecting to the SQL server to get the non-spatial data related to that item, and then merging the two result sets, one from the GIS system, one from the SQL database, into one final piece of consolidated data that has all the information we need. So that is obviously a way more time-consuming scenario in terms of the development effort. When you put everything inside the SQL database, now your development is more streamlined and you're only working with SQL basically. And that becomes a very important advantage as you will see in the next 2 slides. So again, why this is such a great idea? Because now what I'm going to show you is how you actually query spatial data and how you work with spatial data in the context of SQL statements, or using SQL statements, or using SQL syntax. So you don't have to learn a new programming language like for manipulating spatial data. You're just writing SQL, okay? And it's not just that you're writing SQL, you're mixing spatial and non-spatial data types very freely and very elegantly together, and also spatial functions and non-spatial functions like aggregate functions, like computing the sum or the count or the mean or the maximum or the minimum in the SQL language now is interchanged or mixed in a nice way with spatial features or spatial functions like finding the length or the area or the adjacency test for spatial data. Here is an example of what I'm referring to. So let's assume you have a spatial database, which means you have a SQL database that has spatial data augmented into it. And now you can write queries like this. I have put for you here snippets of 3 queries, or you could think of them as being one big query. So if you look at the first one, it's going to be select star from this table where distance, this is a spatial function, from me to the coffee shop location is less than 1,000 meters. So coffee shop log is a column that exists in this table I'm querying, and its data type is a spatial data type. Okay? Distance is a spatial function. Me is going to be a value I pass that also has to be of a spatial nature. But the rest is plain SQL. It's just the SQL language you've learned in database 1. Same thing for the next example. Select star from this table, where the distance from me to the coffee shop is so and so, like the first part we were looking at in the first bullet, and you add, and where touches the coffee shop location touches this street. So this is the adjacency feature we were talking about. Okay. So now distance is a spatial function, touches a spatial function. Me is a value of a variable I am passing of spatial data type. Coffee shop column is the column name, or coffee shop lock is the column name, and street is also some value I am passing that's going to be of spatial nature. Okay. The rest again is SQL. Okay. Or I could augment that by setting another condition where, inside, coffee shop location is inside the city area, which means, this is containment. So this coffee shop is in this city, where the city name is so and so. Okay. So now you see we're mixing SQL and spatial, and I'm still sticking to the SQL syntax, which turns out to be a great advantage because it simplifies the development of spatial applications a lot. A spatial application like Uber could not have existed without this level of simplicity when we actually manipulate spatial data. Here is another example where again I'm mixing or doing aggregate functions and mixing spatial and non-spatial functions. So I'm calculating basically the price of my plot, the area of my plot multiplied by the price per acre plus the area. The area is an area computation from a polygon, and the area of what intersects between my plot and the forested area multiplied by some value per acre, and I subtract from that some value which has to do with how far my plot is from the power line. So again here distance is a spatial function, intersect is a spatial function, area calculation could be thought of as a spatial function or not, because it's basically the area of a polygon, so you could think of it as a non-spatial. It's basically a mathematical function or an aggregate function in SQL. Okay. Value per acre obviously is not spatial, it's just a number. Cost of power line laying is a multiplication. Here is again a simple mathematical multiplication that you would do in a typical SQL. So again here you see a nice mix between spatial and non-spatial features. So here are some takeaways. Spatial functions are functions performed on spatial data. There are 3 broad categories of spatial functions: proximity, adjacency, and containment. In other words, if you go to any spatial database, which means it's a SQL database that has spatial features, you're going to ask about two main things. First of all, what are the basic data types that exist there? And you need to have 2 basic data types: a data type to represent points and a data type to represent polygons or regions. Okay? And then you ask about something else. How do you do proximity, adjacency, and containment computations? Okay? The 3 are important for you. They are the 3 basic building blocks that you need to actually get any decent spatial functionality out of your spatial database. Okay? So you need proximity. It doesn't have to be called like this. It could be called something else. Okay? But you need the feature of getting proximity calculated, adjacency checks, and containment checks. Proximity spatial functions answer the question, is X close to Y? Okay? Example usage, in Uber and Kareem, who's the closer driver to me? So this is a proximity calculation. Adjacency spatial functions answer the question, is X neighbor of Y? Okay, is this adjacent to this? The border of this touches the border of that. Okay? We use this a lot to answer many higher level queries. Like, for example, if streets are encoded as lines and building as polygons, this is how I answer the query, is there a hospital in street Y? Because the polygon that represents the hospital X will touch the line that represents street Y. Okay? So if they touch, they are adjacent. And if they are adjacent, then the hospital is in this street. This is how to think of it. The next one is containment. Containment spatial functions answer the question, is X in Y? So for example, if Cairo is a polygon and universities are also polygon, and you like to answer the spatial query, which universities are in Cairo, this is really containment because they reside within Cairo. They are inside the polygon of Cairo. Okay? So while the higher level question is going to be something like which universities are in Cairo, when you translate it to the spatial query, you're going to be testing for containment basically. Now we come to the spatial database offerings. What exists in the market to enable you to develop an application like Uber or Kareem. Okay? Now, historically, as I mentioned, we used to have separate GIS systems. These guys are now a legacy. Okay? They have been merged into databases. So what you need to look for is an extension for the database that you are using that adds to the database spatial data types and spatial functions. So for example, if you're using Oracle, you're going to go and download something called Oracle Spatial, which is an extension to the Oracle database that gives you the spatial data types and the spatial functions. If you're using Microsoft SQL Server, you download something called ESRI SDE, and this is the most popular one. This is by a separate company. It's an extension to SQL Server that adds spatial data types and spatial functions to SQL Server. Now, in our case, we're using PostgreSQL, and the most popular, actually, extension for PostgreSQL that supports spatial data types and spatial operations is PostGIS. And that's the one you're going to be using in your project. Now, PostGIS, by the way, implements an international standard. It's called the OpenGIS standard, okay? Now, is a very rich standard. So when it comes, for example, to the data types, it doesn't just support points and polygons, which are two basic ones you need. It also supports lines and geometry collections, and multi-lines as well, and multi-polygons and multi-points. So it supports a lot of types. And it has hundreds of spatial functions. So I'm going to show you some of them, just that you get a sense of how you work with them and you see how flexible PostGIS is. So the first function we're going to look at, and by the way, all PostGIS functions starts with st underscore, and it's called the intersects function. This is again a spatial function. You give it two polygons, and it will tell you if the polygons intersect or not. Okay, so I'm again showing you here kind of review of these functions. So obviously here A and B you would be retrieving from some columns that you have in your table that are of a spatial type. And each one of them is actually a polygon, okay? This could be like, for example, land usages or different buildings in the city or different buildings intersecting with empty lands and so on. Or one represents, A represents buildings, B represents empty lands. Something like this, okay? So the point is you have two polygons and you would like to test if they intersect or not. Now, so the figure on the left will return to you true because the A and the B, the red and the blue polygons intersect, and the figure on the right, they don't intersect, so it will turn to you false. Here is another two related spatial functions, contains and within, okay? So if you're asked, does A, which is the one in blue, contains B, and the answer is yes. If you ask, is B within A, and the answer also is yes. Both of them will return true because of how the figure is laid out in front of you here. There is also the touches. This is for adjacency. When we say A touches B, A and B on the left are polygons. The result is going to be true because they touch. And touches also support lines. So if A and B are lines, it will also give you the answer as yes. And as I mentioned, this is an important function because if you're trying to do any kind of path planning where we would like to go from some starting point to a destination, going through streets, we have to go through streets that touch us, that are intersecting, okay? For example, in Madinat Nasr, if you know Madinat Nasr, Makr Mabed and Hassanin and Abbas al-Aad do not intersect, okay? And same thing for Tagamma, you know, Gamal Abdel Nasser, which is the street that has, you know, the Gulf entrance, Tamiya Gulf, and so on, and Shari'a Tis'in, they don't intersect. So if you would like to go from Gamal Abdel Nasser to Shari'a Tis'in, then you need to find intersecting streets. Something that intersects with Gamal Abdel Nasser, that perhaps intersects with something else, another street perhaps intersects with a third street, and finally that one intersects with the same street. Okay? So touches is a very important function that we keep using in the spatial world. Another one is crosses. Crosses is interesting because you know, crosses will return true if A and B cross, which means they go from one side to the other. They don't just touch, they cross. Okay? That's again something you could use when you're doing path planning in a city. So if you'd like to say that, you know, I can cross this street but not go into it, then this is the function you use, and here the result will be true for this A and B setup. A third one is calculating distance. This is related to proximity, but this is a kind of an advanced calculation because A and B here are polygons, and what you pass as a third parameter to this function is a distance, and it returns to you true if A and B are within this distance. Now, to do this calculation properly, the algorithm will find the closest point that it needs to be comparing with in A and in B, okay, which is the one that has a circle here in the slide. And then it will check the distance between those 2 points, and if it is within this distance, it will turn to you true. Another nice feature in PostGIS is this testing for what's called bounding boxes, okay? So the bounding boxes check operator is the 2 ampersands together without a space between them, and they check if the bounding boxes are actually interacting, and interacting here includes one being within the other or there is an overlap between them. So we will come to the notion of bounding boxes later on because this turns out to be a very important simplification we could make to have our computations done as fast as we can. So it speeds up computations to be working with bounding boxes instead of working with polygons. So basically, think of this as a box. You're testing whether the boxes are interacting or not. Well, as you see on the left, you have 3 types of interaction, one of them within the other, or there is an overlap. On the right, you see that the bounding boxes are not overlapping and they're not within each other, so the bounding box operator, the 2 ampersands, would return false. This is an example of what I was referring to, why bounding boxes are important. If you're trying to do any kind of computation between the red triangle and the blue circle, well, if you work without the bounding boxes, the computations are going to take more time. But if you work with the bounding boxes, then it boils down to being comparing rectangles, which is the bounding boxes. So the bounding boxes here will tell you that there is an interaction, you know, A and B using bounding box operator will return true because there is an overlap between the bounding boxes. Notice that this is a bit deceiving because the objects themselves are not overlapping. The red triangle and the blue circle are not overlapping, but their bounding boxes are because of the nature of the triangle, okay? Now, if you actually test, you know, whether A and B are intersecting, obviously the result is false because the circle and the triangle are not intersecting, but the bounding boxes are, okay? So this type of checks that we are seeing here is used to speed up computations as we will see later on. What other spatial functions we have? We have computations of length, area, okay? And we have 2 functions in PostGIS to convert between the internal spatial data type and textual representation to be able to display it to the programmer on the screen, or at least to do some kind of debugging to understand the values we're working with. So let me show you an example of using all of that. So here I'm going to create a table called points, and it has 2 columns. The first one is called PT for point, and its data type is geometry. And the second one is called name, and it's a varchar. When I'm inserting into this points table, I will use this point function and I will pass it x and y coordinate values. Okay, here I'm not using longitude and latitude, I'm just using simple x and y. So I pass it 0.00, 0.50, and 0.05 for the origin x-axis and y-axis coordinates. Okay, now let's say I would like to write a SQL statement that manipulates points. So I say select name and then st, that's PostGIS function, as text point column. That will display the content of the point column as text. Otherwise, you will see gibberish displayed to the screen. And you call, or I'm calling here the st underscore distance, that proximity calculation between point and 0.55. So pt, point, is actually the column. So this will, just like you understood from the SQL study before, this will be applied to every value in the point column. Okay? And then from points, the table name. When I run this, this is what I'm going to get. I'm going to get name as text distance, and as you see, the name is origin, the 0.00. This is what I inserted into the table. X-axis 0.50, y-axis 0.05, and then I calculate the distance using the spatial function distance that I have showed you in the previous slide, and that's the computation of the distance. 7.075 and 5 is actually the distance computed. Here are more examples of doing or working with PostGIS. Okay, let's try to read the query first. It says select sum st underscore length from the geometry divided by 1,000 as kilometer roads. You see I'm mixing SQL and Spatial here nicely from Cairo roads. What am I trying to do here? I am summing up the lengths of all these streets in Cairo. Okay, so sum is an aggregate function, SQL aggregate function. St underscore length is a spatial function that works on the spatial column called the geometry, and it converts the geometry into a length because the geometry type is going to be some kind of a line. So I get the length of the line, and I sum up all the lines, dividing by 1,000 to get it in kilometers. Okay, and I label it as kilometer roads in the output. Here is a second example. Let's again try to read the SQL first. Let's say select st underscore area, so I'm computing the area of some polygon, the geometry, divided by 4,200, that's basically converting it into hectares or faddans, from city where name equal to Cairo. So basically I am calculating the area of Cairo. Okay, again note here that the mix is quite nice. You know, I'm basically writing SQL, except now I have these spatial functions. The next thing we're going to look at is this notion of spatial join. Now you have studied joins in database 1. It's a very important concept because we can use it to actually connect two or more tables together to get a more consolidated data set. Now we were going to use the same concept except applying it to spatial data. Now when you join on spatial columns, you'll have to use a spatial function to qualify the row from every table that you are checking to decide whether it's going to be included in the result set or not. And that's what you see here in the second bullet. Let me read. It says select a.var, b.var2 from a, b. So these are the two tables I am joining on, or trying to join together. And then I need to provide a condition for the join. And since a.var1 and b.var2 are both spatial data types, I cannot directly manipulate them by saying a.var1 equal to b.var2. It doesn't work like that. I have to use a spatial function. And here I decide to use intersect. So as long as a.geometry intersect with b.geometry, I'm going to include the row. So obviously here this is a little bit more flexible than what you have learned as a join strategy, because I could use any spatial function that will return a Boolean result to be my joining function, or to be the condition according to which I make the join. Okay, so I could use any function in PostGIS that returns a Boolean result, and that will be what gets tested for every row from A and every row from B to decide whether we should include that combination of a row from A and a row from B into the result set or not. So here is an example of this. If I try to find out all the coffee shops located within 250 meters of a hospital, so I select from the hospitals table and the shops, or the shop table, okay? or the coffee shop stable. And my condition is like this. I use the within function that we have seen before, and I pass it the hospital's geometry and the coffee shop geometry, and I say within 250 meters. Okay, so now you see here my joining condition is the within function, because it's returning true or false based on whether the hospital and a specific hospital and a specific coffee shop are within 250 meters from each other. Okay, so this is an example of doing a spatial join. Now we come to the very important topic, which is the reason why we've done most of this introduction, apart from the fact that you're going to do a project on spatial databases. We're going to come to the very important topic of spatial indexing, this notion of creating an index on a spatial data structure. Why do we need a spatial data structure? Because regular data structures or non-spatial data structures are created to store one value. While in the case of a spatial index, you're going to be storing a location, a longitude and latitude, some X, Y, and Z. So it's a triple or a double value or a pair of values that represent a location. And consequently, you need, when you're actually storing this location, to have the data structure understand the essence of the location. That when you're actually asking containment or adjacency or nearest neighbor, we need the indexing data structure to help you to answer those queries. So the issue is not about storing. You could store it any way you like. The point is, the operations supported by the index should tailor to the spatial needs, which again, the basic set of needs are being able to calculate proximity, being able to calculate adjacency or confirm adjacency, and being able to confirm containment. Okay? And for that reason, we need a data structure that understands locations. And it is efficient. So efficient here really in our world means O of 1 or O of log n. That's acceptable. Beyond that, it is not acceptable. Okay, it's going to be too slow. And what we're actually going to look at here, which is the most common indexing data structure that exists in the spatial databases world, is the R3s. Now, R stands for region, and this is nothing but a variation of B plus 3s. So everything we discussed in terms of how the B plus 3 work is applicable here, with one major difference, which is that what we are storing as a key is not a point, is not a data point, it's not a number like what we have seen in the previous lecture. It is actually a region definition. Specifically, it's a bounding box. Okay? In other words, it will have 4 values, x1, y1, x2, y2. So each one of those r's that you see here, r1, r2, r3, r4, r5, and so on, all the way to r19, each one of them consists of 4 numbers. x1, y1 for the upper left corner of the bounding box, and x2, y2 for the right bottom corner of the bounding box. Okay? So this is really the major difference here between R3s and B plus 3s. So I'm not going to go and repeat all the rules for the insertion and deletion of B plus 3s because they are respected here. But I'm going to talk about the differences, which is the notion of storing regions. Because now, since this R's, R1, R2, R3, R4, and R5, it's a quadruple, basically, of values. There are 4 values there, x1, y1, x2, y2. We need to understand when we're going down in this tree doing the insertions, or when we are searching for a value, or when we are actually deleting, how do we go about it? Okay, because it's not anymore a simple single value. Okay, so we will focus on that. Now, everything else, as I mentioned before, including that this is a self-balancing tree, works because the B plus 3 are still rules or invariants are still respected. So in terms of having the tree not skewed, you get that with the R3. In terms of having all the leaves at the same level, you get that with R3, just like we got it with B plus 3. Using the same approach, by setting a minimum and a maximum on the number of keys per node, and doing all the stuff we described before. For example, in insertion, we will favor creating new nodes. In deletion, we will favor compacting the tree. Okay, all of this is still applicable. Okay, and also the notion that in the last row you have the leaves, and in the leaf associated with every key, in this case is going to be one of these R's, one of these regions, you have a reference to where that row exists, still holds. So the pointers coming out from the bottom of this tree are actually taking you to a specific page in the table, okay, that you're building this index on. Like for example, R8, there is an arrow behind it, that will take you to the row that has this R8 entry, okay? So it's going to tell you which page on disk and which row in the page that has this R8 information, okay? So it's the same stuff we discussed before with B plus trees. Now, let me show you an example of constructing an R tree from a given set of polygons, because this is the simplest way I can go about explaining it to show you what is this region business, because we are working here with regions or bounding boxes basically, and that's why it's called an R tree, as I mentioned before. So given these set of polygons, what we're going to do is we're going to compute a bounding box for each one of them. Is that an easy operation? Geometrically, yes. You can do it in a decent amount of time. There are geometric techniques that enable you to find bounding boxes for any polygon. That's what we found now. As you see, every polygon is surrounded now by a bounding box. Now, what I'm going to do, and this is really building up the R tree, I am going to group every set of close by polygons into a bigger bounding box, and that will be my choice. So now I am treating these from this point onward. I forget about these polygons and I'm thinking of them as bounding boxes, okay? And as you see, I have grouped by color here, it is represented, I have grouped every set of adjacent polygons. Sorry, I'm getting confused here, or getting tired perhaps a little bit. I have grouped every set of close by bounding boxes together. So the ones in green are now, for me, close together. The ones in cyan are close together. The ones in red are close together. The ones in blue are close together. Now, how do I actually find these guys? How do I find that they are close together? I could start from the top left corner of my scene and move towards the right and towards the bottom. And as I keep discovering bounding boxes, I group the ones that are close together by considering the centers and the distance between them and other ones. And the ones that are closer together from the center, I will label them as one group. So it makes obviously a straightforward task for me if they are overlapping. Like you see it towards the center of this chart, you have 3 in yellow that are overlapping. A small one and one on the top, and then that one on the top is overlapping with the one on the right. And the same thing for the red ones. So these are very easy to recognize that they belong to the same group because there is an overlap. But if there is no overlap, I could still find out by calculating the distance from the center which ones are closer together, okay? So assuming I'm going to find these ones I have in front of me, what I'm going to do is I will label them together as being one group with one big bounding box. And that's what you see I'm starting to do here. So I am basically grouping the ones that are close together into a bigger bounding box. Now what I'm going to do next is I will continue to do the same thing over and over again. So now I have grouped the 3 groupings on the right into one bigger bounding box because they are closer to each other in terms of the center than anything else. And I did that also for the other 2. And now you end up with your R3. So if you're constructing an R3 from scratch by being provided with a set of polygons, you go to find the bounding boxes for the polygons, and then you look at the centers and compute the distances between all the centers and figure out the ones that are close together, and you again group them into a bigger bounding box, and you keep doing that until you're done, okay? Now, so this is basically the picture that we are looking at here. Now, when I explain this, the first thing that pops out to some students is you could have grouped them differently depending on where you start from. And the answer is yes, but I'm going to establish a convention that I will always start from the top left corner of my scene. Or I could start from the bottom left corner of my scene being my 0, 0. So it doesn't really matter. I have to establish a convention and stick to it. And when I establish a convention, what's going to happen is I will come across certain polygons first compared to seeing other sets if I changed my convention. For example, if I'm starting from the bottom right, I would see the ones in green first. So I will work with them and group them into a bounding box before seeing the ones in blue, which is at the far left of the screen. Okay? So as long as you pick a convention and fix it and don't change it, you will always see the same set of polygons first, and consequently you will always bound them with some bounding box first before seeing the other ones. I hope this is clear, and you will see some examples in the tutorials that covers this specific point, because it's always a source of confusion. Now, if you follow that same convention in the insertion, later on in the search, you will find your target. Okay? You will never be confused. You will never go somewhere else, basically. Okay? And this point will become clear later on. So let's look at this example. If I am looking for this red dot, okay, I'm going to find it. I'm going to find it in the yellow box, which is going to be to the bottom of the R3. Now, this red dot has a coordinate, longitude and latitude, or x and y. Okay, let's just work it simply with x and y. When I ask, starting at the root, about where could this be, just like what I did with a b plus 3, I'm given a value, and I have to decide, should I go follow the first arrow or the next arrow or the third arrow at the root level. I am doing here a containment check. I'm saying, okay, does this exist within this bounding box, or within that bounding box, or within the other bounding box, the third bounding box? So I will follow the first arrow, the one that I have put a red X beside it. Why am I following that one? Because containment-wise, when I was inserting the red dot, I must have followed that path. So I will go and search for it in that region, okay? In that within that subtree, okay? It's not going to be in the next one. It's not going to be in the third one. It's going to be in this one that I'm labeling with a red X, okay? And I do the same thing over down here in the where you have the green X. So again, I will do a containment check. Where would the red dot be? And again, I will be told or I will figure out from checking the containment that it is within the yellow bounding box. So I will go down to the 3 yellow bounding boxes until I find it. Okay? I followed the same strategy in insertion, and that's why it ended up being there. So when I now follow the same strategy in the search, I should also find it there. I hope this is clear at this point. Another thing we have to note is the n value. So let's say I am giving this set of bounding boxes. If I say that my R3 n is equal to 4, that means at most I could put 4 regions in a bounding box. So when I'm grouping, or when I'm collecting bounding boxes to be put in a bigger bounding box, I could never exceed 4. Okay, that's what you start to see here in this arrangement of bounding boxes. I picked a bounding box for 4 of the bounding boxes that already exist, and this keeps going on when I'm building up the R3. You see this here now. When I'm collecting my bounding boxes, I am again sticking to the rule of maximum of 4, and it is applicable everywhere. Okay. So n here equal to some number, some value equal, say it equal to 4, that means 4 regions, that means 4 bounding boxes, regardless of the level you're actually at in the R3. And that's another set of 4 picked up, and another set of 4 picked up. So let's talk about the R3 structure. So again, we have internal nodes and we have leaf nodes. What's in the internal nodes is basically regions. Now, the thing is, R3 thinking, or the R3 way of thinking in the internal nodes, you have a region description, and everything that is below this region are contained within this region. Okay? So this is different. It deviates from the logic of B+3 or binary search trees in general, which is that you go to the left, it's smaller than you go to the right, it is bigger or equal to. Well, in R3, when you go down, you're going to nested bounding boxes within the bounding box of the parent. Okay? So if the parent starts from 0, 0 to 100, 100, what you will see inside it at the next level in the R3 are bounding boxes within the bounds of 0, 0 to 100, 100. So you could see like perhaps 10, 10 to 20, 20, 30, 30 to 40, 40. All of them are within the range of 0, 0 to 100, 100. Okay? So there is nesting happening one level down as you go in the tree. There is always continuous nesting. Okay? Now, R3's leaf node is holding what's called the MBR, the minimum bounding boxes. Okay? So when we are actually going above the leaf level, we are seeing bounding boxes that are made based on our choice of the MBRs that we picked at the leaf level or at the basic level when we were constructing the R3 at the leaf level. Okay, so this notion of minimum bounding boxes is important because usually we start with polygons. What we are inserting really in the R3 is a polygon, but we don't insert the polygon. We insert the bounding box around the polygon. Okay, but now when we start to have more than one polygon, the question is, where should we put the polygon? Where should we put the new entry? Okay, which bounding box it will go into? And the rule is, we will always respect is, we would like to increase our bounding boxes as little as possible, because the less overlap between the bounding boxes, the better, because this enables us to get branching, which enables us to get the log n performance. Okay? So, when I'm trying to insert in an R3, I will start from the root, just like I start in the B+3, but I'm checking bounding boxes. And my goal always is to find the location for the new entry in an existing bounding box. Okay? If I don't find that, I'm going to increase my bounding boxes. So let me show you a simulation of this. Okay? Now again, the question is, where should we insert it? And let's look at this example. Now in this example, I have 4 bounding boxes, M, N, O, and P. If I get this new entry, that was a polygon and I created this bounding box for it, the most important question here to answer, to be able to get the nice performance is, where should this go? Okay? Now, theoretically it can go anywhere. It's not contained within any one of them. So it could go anywhere. I just need to change any one of them to make it encompass or contains this new green bounding box. But the rule is going to be, I will pick the bounding box that will require the least amount of increase in its total area to include this green one. Okay? So let's do this simulation. If I make it inside the M, I will have to make the M this much bigger. If I make it inside the N, I will have to make the N this much bigger. If I make it inside the O, I have to make the O this much bigger. If I make it inside the P, I have to make it this much bigger. Now you get the idea that if the new entry is not fitting in my bounding boxes, my existing bounding boxes, in the leaf level, I am working at, in the specific node in the leaf level I am working at, trying to insert this new entry. I will change the bounding boxes, one of them, to encompass this new entry. Now, the problem is, the more intersection between the bounding boxes, the less branching I will have in the future. The less the intersection between the bounding boxes, the more branching I will have in the future. So I need to increase the size of the bounding box that will have the slightest or the smallest increase. Okay? And this is really the only difference between R trees and B plus trees, that it will involve bounding boxes selection. And this is actually, you go all the way till the leaf, and then if you find a location for the entry, just like in the case of B plus 3, you put it there. But if you don't find the location and you're going to create a bounding box, then you got to propagate upward your changes in your bounding boxes to make sure that you're always contained, or the new entry is always contained in the parent. Okay? And that gives you a choice at every level all the way till the root, that you're always changing the bounding boxes, but you look for the one that has the smallest change, which was the P, I believe, in the example we were looking at. Okay? And this is what I try to highlight here, that the fewer rectangles intersected, the better. Okay? So, because again, that means you have disjoints areas, and consequently, when you're making a decision, should I go here or there, the decision is clear. You are going to go to one of them and leave the other three. So the takeaway here is that an R tree is a modified B plus tree for indexing spatial data. An R tree enables fast execution of exact value on polygons and range queries, as well as proximity, adjacency, and containment spatial queries. Now, how it is the case, you will see some examples in the tutorial, because the way that we are nesting things will enable us to calculate very fast the three basic operations that we need in the spatial world. Now, how you actually create a spatial R tree in Postgres or PostGIS? First, you have to have PostGIS installed inside Postgres. And then you actually do the following. You use the statement, like for example here at the bottom, I say create table points, point geometry, and name varchar. This is the same table we looked at before. And then I will create the index on points, and I say using just, and I pass it the column that is of spatial nature, okay, or the spatial data type. And this gets me a R tree created. So I'm not creating the R tree directly like what we've seen with B plus trees. I'm actually using the GIST library, and I'm passing it the name of the column that is of spatial nature, and it will create the appropriate data structure. In this case, it's going to be an R tree. Okay? Now, by the way, GIST is an extension to Postgres. It's a library that looks at the past column data type and creates the appropriate index based on the data type. Not based on the data stored in the column, but based on the data type. So if it's spatial, it's going to always create R3. Okay? These are the references for today's lecture. I have included for you a Wikipedia page on R3s, and it's also included in your textbook on page 683 to 686. And you have a link to the PostGIS and a list of full functions in PostGIS that you will need for your project. Now, for the exam, you will be responsible only for the functions I'm showing you here in the lecture slides, and if I want you to use any other function, I will be giving it to you in the exam as an external documentation or aid sheet. So I don't expect you to know all the hundreds of functions in PostGIS, but I want you to know the basic ones and how you can actually code it and how you can construct an R tree, and how the R tree is actually slightly different from the B plus tree in its storage of regions instead of values.